Hello, my name is Bill Johnson. Welcome to this presentation on multi-dimensional ground reaction forces and moments from wearable sensor accelerations via deep learning, or in other words, how to replace your force plate with cat photos. We know that what we measure in the lab doesn't always translate to what actually happens during a game. And wouldn't it be great if we could take measurements of ground reaction forces and moments in the field in real time? Now, the traditional approach to this, of course, has been via linear statistics, but we wondered if new data science methods, specifically deep learning, could improve on these models, because this might open up opportunities for on-field estimates of knee loading and perhaps even provide a live indication of ACL injury risk. But what is deep learning? Deep learning is an example of an artificial intelligence system which is based on a learning model rather than a task-specific algorithm. And from about 2012, these models started to get really good at classifying images. Under the hood, what the models have in common is a framework of hidden layers, and the better ones for image classification have a front end of sliding windows called convolutions. To identify the cat, for example, that model was trained with 1.3 million photos against 1,000 object classifications. If we could represent our biomechanics data in a way that these classifiers could handle, maybe we could reuse their accuracy without needing 1.3 million trials of our own. And to do this, our first step was to represent movement with 8 marker trajectories and build a model which can relate these to ground reaction forces and moments. And immediately we hit a wall, because of course the difference between the cat image and our marker trajectory data is that, and we're using sidestepping, is that our data includes the 4th dimensional time, and our model is only good for matching 2D images. In other words, we need to flatten space-time. To do this, we're going to fake up an image. So this blurry color image is one trial. We've made the 8 markers the width, and it's 125 frames of video, the height, and we're going to map the XYZ coordinates onto the RGB color space. And now what we have is all of our trials as images. This matrix contains the same trials as that earlier animation, so we flattened space-time and we've solved the input problem to our CNN. But we still have an output problem, because our model is a classifier, which means it's going to tell us how much each trial corresponds to the 1,000 object labels that it knows about. To fix this, we need to do some surgery on the softmax layer on the right hand side. So we'll slice it off and replace it with a Euclidean loss, and now our CNN becomes a multivariate regression network. In other words, it now predicts waveforms, which is exactly what we need. We have a model which can predict all 6 vectors of ground reaction forces and moments from our flattened marker-based motion capture. So let's look at how this model performs. But just quickly before we do, worth pointing out, these are all multi-data captures, which means we can compare what was recorded by the force plate with what is being predicted by our model. And we're reporting the mean of the 3 forces and the mean of the 3 moments. And if we look at our 8 marker model, we can see that it's approaching 1 for both GRFs on the vertical and GRMs on the horizontal, but interestingly we found a 4 marker configuration that achieved nearly the same results. Now, although outdoor volume spaces are getting larger, marker-based motion capture is not exactly game practical, and we sold you a presentation about wearable sensors. So we used the 4 marker results to tell us where to put 4 sensors. But you guessed it, again, straight away we hit a wall, because first we have no acceleration data. So we need to create synthetic accelerations from the marker trajectory archive using double differentiation. And second, each sensor has an independent coordinate system, which means all the accelerations point in different directions. And so first up, we're going to try acceleration magnitude, or Euclidean norm, to combine the 3 directional components into one. Hence the fuzzy images go on black and white, because we've thrown away the color information. And third, to give our new model a leg up, we're going to use a technique called double cascade, and this means that we're reusing the weights from the marker trajectory model as we build our acceleration model, and this should make it more accurate. So let's have a look at this norm model. Well, it does achieve greater than 0.85 for moments and over 0.93 for forces, but notice the error bars, and particularly that they're much wider for moments. Perhaps are we throwing away too much information by combining the three dimensions into magnitude only of acceleration? Could we improve the accuracy and reduce the error if we find a way to retain some or all of that directional information? So we're going to use principal component analysis to give us a rotation matrix which will align the 3D accelerations in the direction of maximum energy. And you can see that PCA does retain more information because the trial images are getting color. And these are all the trials again. And so if we look at the results, we can see that the PCA model, yes, has quite an improved GRM, but particularly the error bars are shorter as well. This means that the effort to retain directional information was worth it. And the PCA model, so what we're doing here is we're predicting GRF and Ms from accelerations from 4 sensors, and we're getting correlations above 0.9 for both GRF and GRM. These results compare really well with the literature, and they improve on our 3-sensor version that you may have seen in the conference abstract. But here's the thing, it's not about the numbers. Sure, we are just a couple of small steps away from accelerometer-driven analysis in the field. But what this project really delivers is a deep learning workbench for biomechanics, because we all work in 3 dimensions plus time, and we're all limited by the number of trials we can capture. Up to now, deep learning has been off limits because we were told we needed millions of samples, and most of the models are classifiers. They just tell us how much our image resembles a cat or a particular image, good, better, best. And so often what we did was dumb our data down to suit these off-the-shelf machine learning applications. So instead, yes, we needed to go under the hood. We've hacked CNN inputs and outputs, but in doing so we're maintaining multi-dimensional fidelity and creating personalized predictions. I really hope that this presentation has given you some ideas of the latent possibilities that exist within your own biomechanics archive. Thank you for your attention. If you'd like more information, we've got models and figures and more animations at our GitHub site. You can get there at digitalathlete.org.